According to the National Electrical Code, the minimum number of grounding electrodes required for premise wiring systems that are required to be grounded is 1. Let's consider a small dwelling with a Ufer grounding electrode system. In this scenario, the Ufer grounding electrode system alone meets the National Electrical Code requirement for a minimum of 1 grounding electrode. Therefore, additional grounding electrodes are not required, and it is not necessary to drive ground rods. However, it is still necessary to bond to the cold water and any other system that requires bonding. Now consider a storage building with a Ufer grounding electrode system. In this scenario, the Ufer grounding electrode system does not have a connection to a water system. Therefore, an additional grounding electrode is required to meet the National Electrical Code requirement for a minimum of 1 grounding electrode. In this case, it is necessary to drive a ground rod. In both scenarios, the minimum number of grounding electrodes required is 1. However, in the second scenario, an additional grounding electrode is required because there is no connection to a water system. To elaborate, the National Electrical Code, or NEC, sets the standard for safe electrical installations. Grounding electrodes play a crucial role in protecting people and property from electrical hazards. A grounding electrode provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices, like circuit breakers, to quickly trip and clear the fault. The Ufer ground, also known as a concrete encased electrode, is a grounding electrode that consists of a metallic conductor, typically bare copper rebar or wire, encased in concrete. It is often used in building foundations. The concrete provides good contact with the earth, making it an effective grounding electrode. Bonding, on the other hand, connects different metallic parts of an electrical system to create an electrically conductive path. This ensures that all bonded parts are at the same electrical potential, reducing the risk of electric shock. The NEC requires bonding of metal water piping systems, metal gas piping systems, and other metallic elements that could become energized. In the case of the small dwelling with a Ufer ground, the Ufer ground itself satisfies the requirement for a single grounding electrode. Because the Ufer ground is in direct contact with the earth through the concrete foundation, it provides a sufficient path for fault current. It's crucial to bond the metal water piping system to the grounding electrode system. This bonding ensures that if a fault occurs, the fault current can safely flow back to the source through the grounding electrode system, tripping the circuit breaker and preventing electrical shock hazards. In the storage building scenario, the situation is different. Even though the building has a Ufer ground, there is no connection to a metal water piping system. The NEC generally requires a supplemental grounding electrode when the primary grounding electrode is not supplemented by a metal water pipe electrode. Since the storage building lacks this water pipe connection, a ground rod or other approved grounding electrode must be installed to supplement the Ufer ground. This ensures that there is a reliable grounding path even if the Ufer ground's effectiveness is compromised. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground plates are metal plates buried in the earth. Metal underground water pipes, when in direct contact with the earth for at least 10 feet, can also serve as grounding electrodes. When using ground rods, the NEC specifies requirements for their installation. They must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. If rock bottom is encountered, the ground rod can be buried horizontally in a trench that is at least 30 inches deep. In situations where multiple grounding electrodes are used, they must be bonded together to form a grounding electrode system. This bonding ensures that all grounding electrodes are at the same electrical potential, providing a more effective path for fault current. The size of the grounding electrode conductor, which connects the grounding electrode to the electrical system's grounding bus bar, is determined by the size of the ungrounded conductors of the electrical service. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. It's important to remember that the grounding electrode system is just one part of a comprehensive grounding and bonding system. Effective grounding and bonding are essential for electrical safety. A properly installed and maintained grounding and bonding system helps to minimize the risk of electric shock, fire, and equipment damage. Grounding and bonding work together to provide a safe electrical system. Grounding provides a path for fault current to flow back to the source, while bonding ensures that all metallic parts are at the same electrical potential. This combination minimizes the voltage difference between conductive surfaces, reducing the risk of electric shock. The NEC is updated every 3 years, so it's essential to stay current with the latest requirements. Local jurisdictions may also have additional requirements, so it's important to check with the local authority having jurisdiction, or OJ, to ensure compliance with all applicable codes and regulations. Electrical work should always be performed by qualified and licensed electricians. Working with electricity can be dangerous, and it's important to have the knowledge and skills to perform the work safely and correctly. Improperly installed or maintained electrical systems can pose serious hazards. The role of the grounding electrode system is primarily to provide a connection to earth for the electrical system. This connection to earth helps to stabilize the voltage of the electrical system and provides a low impedance path for fault current to return to the source. When a fault occurs, such as a short circuit between a live conductor and a metal enclosure, the fault current will flow through the grounding electrode system back to the source. This high fault current will cause the overcurrent protective device, such as a circuit breaker or fuse, to trip, disconnecting the circuit and preventing further damage or injury. Without a proper grounding electrode system, the fault current may not be able to flow back to the source quickly enough to trip the overcurrent protective device. This could result in a dangerous voltage buildup on metal enclosures, creating a shock hazard. In addition to protecting against electrical shock, a grounding electrode system can also help to protect against lightning strikes. When lightning strikes a building, the surge of current can cause significant damage to electrical equipment and wiring. A properly installed grounding electrode system can help to dissipate the lightning current into the earth, reducing the risk of damage. There are different types of grounding electrodes that can be used depending on the site conditions and the requirements of the NEC. The most common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as Ufer grounds. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. They are a relatively inexpensive and easy to install grounding electrode. However, they may not be as effective in areas with high soil resistivity. Ground plates are metal plates that are buried in the earth. They provide a larger contact area with the earth than ground rods, making them more effective in areas with high soil resistivity. However, they are more expensive and difficult to install than ground rods. Metal underground water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. However, they must be electrically continuous and free of insulating coatings or joints. Concrete encased electrodes, or Ufer grounds, are made by encasing a metallic conductor in concrete. They are typically installed in the building's foundation or footing. Ufer grounds provide a very effective grounding electrode because the concrete provides a large contact area with the earth and helps to maintain a low soil resistivity. The NEC specifies the requirements for the installation of grounding electrodes. The requirements vary depending on the type of grounding electrode being used. For example, ground rods must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. If rock bottom is encountered, the ground rod can be buried horizontally in a trench that is at least 30 inches deep. Metal underground water pipes must be in direct contact with the earth for at least 10 feet and must be electrically continuous. Concrete encased electrodes must be encased in at least 2 inches of concrete and must be located within the bottom 2 inches of the footing or foundation. In addition to the grounding electrode, the grounding electrode conductor is also an important part of the grounding system. The grounding electrode conductor connects the grounding electrode to the electrical system's grounding busbar. The size of the grounding electrode conductor is determined by the size of the ungrounded conductors of the electrical service. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be made of copper or aluminum and must be protected from physical damage. It must also be installed in a continuous length, without any splices or joints. The grounding system is an essential part of any electrical system. It protects people and property from electrical hazards. It is important to have a properly installed and maintained grounding system. Electrical work should always be performed by qualified and licensed electricians. Working with electricity can be dangerous, and it is important to have the knowledge and skills to perform the work safely and correctly. Improperly installed or maintained electrical systems can pose serious hazards. Remember that the National Electrical Code is a comprehensive document, and this explanation provides a simplified overview of some key requirements related to grounding electrodes. Always consult the latest edition of the NEC and local codes with specific requirements and guidance. It is also important to consider the specific conditions of the site and the electrical system when designing and installing a grounding system. The goal is to create a safe and effective grounding system that protects people and property from electrical hazards. The information presented here is for general educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified and licensed electrician for any electrical work. Grounding electrode systems are not static installations. They should be inspected and tested periodically to ensure that they are functioning properly. Soil conditions can change over time, which can affect the resistance of the grounding electrode. Corrosion can also damage grounding electrodes and conductors, reducing their effectiveness. Regular inspections and testing can help to identify potential problems before they become serious hazards. There are several methods for testing grounding electrode systems. One common method is to use a ground resistance meter, also known as a ground tester. A ground resistance meter measures the resistance between the grounding electrode and the earth. The lower the resistance, the more effective the grounding electrode. The NEC recommends that the resistance of a grounding electrode system should not exceed 25 ohms. If the resistance is higher than 25 ohms, the grounding electrode system should be improved. This can be done by driving additional ground rods, installing a ground plate, or improving the soil conditions around the grounding electrode. Another method for testing grounding electrode systems is to use a clamp-on ground tester. A clamp-on ground tester measures the current flowing through the grounding electrode conductor. This method can be used to identify problems such as a broken grounding electrode conductor or a loose connection. In addition to testing the grounding electrode system, it is also important to inspect the grounding electrode conductors for any signs of damage or corrosion. Grounding electrode conductors should be replaced if they are damaged or corroded. Maintaining a proper grounding electrode system is essential for electrical safety. Regular inspections and testing can help to identify potential problems before they become serious hazards. Always consult with a qualified and licensed electrician for any electrical work. The function of a grounding electrode is to provide a stable reference point to earth for electrical systems. This is crucial for safety and proper operation. Firstly, it limits voltage to ground. Without a grounding electrode, the voltage of an electrical system with respect to earth could fluctuate significantly. This fluctuation could create a shock hazard and damage equipment. The grounding electrode helps to stabilize the voltage, keeping it within safe limits. Secondly, it provides a path for fault current. In the event of a fault, such as a short circuit, the fault current needs a path to flow back to the source. The grounding electrode provides this path, allowing the overcurrent protective device to trip and clear the fault. Thirdly, it protects against lightning strikes. Lightning strikes can cause significant damage to electrical systems. The grounding electrode provides a path for the lightning current to flow to earth, reducing the risk of damage. Fourthly, it minimizes electrical noise. Electrical noise can interfere with the operation of sensitive electronic equipment. The grounding electrode helps to minimize electrical noise by providing a low impedance path for noise currents to flow to earth. Fifthly, it ensures proper operation of equipment. Some electrical equipment requires a connection to earth for proper operation. The grounding electrode provides this connection, ensuring that the equipment operates correctly. The selection of a grounding electrode depends on several factors, including soil conditions, the size of the electrical system, and local codes. The most common types of grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes. Ground rods are typically the most economical choice for grounding electrodes. They are driven into the ground and connected to the electrical system with a grounding electrode conductor. Ground plates are more expensive than ground rods, but they offer a lower impedance path to ground. They are buried in the earth and connected to the electrical system with a grounding electrode conductor. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements. The pipe must be metallic and in direct contact with the earth for at least 10 feet. The pipe must also be electrically continuous. Concrete encased electrodes, or Ufer grounds, are installed in concrete foundations. They offer a very low impedance path to ground. The grounding electrode conductor connects the grounding electrode to the electrical system. The size of the grounding electrode conductor depends on the size of the electrical system. The NEC provides tables that specify the minimum size of the grounding electrode conductor. The grounding electrode conductor must be made of copper or aluminum. It must be protected from physical damage. The grounding electrode system is a critical component of any electrical system. It is important to select the correct grounding electrode and to install it properly. Regular inspections and testing can help to ensure that the grounding electrode system is functioning properly. Always consult with a qualified and licensed electrician for any electrical work. The role of supplementary grounding electrodes is to enhance the effectiveness and reliability of the grounding system, especially when the primary grounding electrode may not provide sufficiently low resistance to earth. Several situations necessitate the use of supplementary grounding electrodes. Firstly, high soil resistivity is a common reason. In areas with soil that has high resistivity, a single grounding electrode may not provide a low enough resistance path to ground. Adding supplementary electrodes, spaced appropriately, helps to reduce the overall resistance. Secondly, inadequate primary electrode. If the primary grounding electrode, such as a single ground rod, does not meet the required resistance to ground, supplementary electrodes are necessary to achieve compliance. Thirdly, critical equipment protection. For sensitive electronic equipment or critical systems, a more robust grounding system with multiple electrodes ensures better protection against voltage fluctuations and electrical noise. Fourthly, large facilities. Large buildings or industrial facilities often require multiple grounding electrodes to provide adequate coverage and redundancy across the entire electrical system. Fifthly, specific code requirements. Local electrical codes or specific industry standards may mandate the use of supplementary grounding electrodes in certain applications. The installation of supplementary grounding electrodes involves a few key considerations. Firstly, spacing. The spacing between supplementary electrodes is crucial. They should be separated by a distance at least equal to the length of the grounding electrode itself to avoid overlapping zones of influence and maximize their effectiveness. Secondly, bonding. All grounding electrodes, including supplementary ones, must be bonded together to form a unified grounding system. This ensures that all electrodes are at the same potential. Thirdly, conductor sizing. The grounding electrode conductors connecting the supplementary electrodes to the main grounding bus must be appropriately sized according to the NEC or other applicable standards. Fourthly, testing and verification. After installation, the resistance of the grounding system should be measured to verify that it meets the required specifications. It's important to consider different types of supplementary grounding electrodes. Firstly, additional ground rods are the most common type. They are driven into the ground and connected to the main grounding system. Secondly, ground plates are buried in the earth to provide a larger surface area for contact with the soil. Thirdly, ground loops are continuous conductors buried around the perimeter of a building or area to be grounded. Fourthly, concrete encased electrodes, or Ufer grounds, can be used as supplementary electrodes if they are not already serving as the primary electrode. It is very important to perform periodic inspections and maintenance to ensure the continued effectiveness of the grounding system. The grounding connection should be checked regularly for corrosion or damage. The resistance to ground should be measured periodically to verify that it remains within acceptable limits. Any necessary repairs or replacement should be performed promptly. In addition to providing a path for fault current and limiting voltage to ground, a properly designed and installed grounding system also helps to minimize electrical noise and interference. This is particularly important for sensitive electronic equipment. By providing a lower impedance path for noise currents to flow to ground, the grounding system helps to prevent these currents from interfering with the operation of the equipment. In some cases, it may be necessary to install dedicated grounding electrodes for sensitive electronic equipment. These dedicated electrodes should be isolated from the main grounding system to prevent noise currents from flowing from other parts of the electrical system. When designing a grounding system, it is important to consider the specific requirements of the electrical system and the equipment that it serves. It is also important to comply with all applicable codes and standards. A qualified and licensed electrician can help to design and install a grounding system that meets these requirements. Ignoring the importance of proper grounding can lead to very serious consequences. Firstly, electrical shock is a major hazard. A faulty grounding system can lead to dangerous voltage on metal parts of equipment, increasing the risk of electric shock. Secondly, equipment damage can happen. Surges and faults can damage sensitive electronic equipment if not properly grounded. Thirdly, fire hazards can arise. Fault currents can cause overheating and fires if the grounding system is inadequate. Fourthly, code violations are possible. Non-compliance with electrical codes can result in fines, penalties, and safety hazards. Fifthly, system malfunction is possible. Inadequate grounding can lead to erratic or unreliable operation of electrical systems. Understanding and implementing proper grounding techniques is not just a matter of compliance, it is a fundamental aspect of electrical safety and reliability. Whether it is a small dwelling or large industrial facility, a well-designed and maintained grounding system is essential for protecting people, equipment, and property from the hazards of electricity.